Okay, thank you very much. So, first of all, I would like to thank the organizing committee that gave me the opportunity to present you today some of our recent results on photoirradiation chemistry, and especially on the redox organic transformation for efficient synthesis of N-Aryl hydroxylamine. And this work has been done with collaboration with my postdoc, Dr. Lykakis. And before I start my presentation, let me show you where we are located. And we are in Thessaloniki, the second biggest city of Greece. And we are located in the north part of Greece. Here is our campus of Aristotle University of Thessaloniki, and here is our the building of our chemistry department. Let me show you two slides for what we are interested for. We are interested for the last more or less 10 years on the metal nanoparticle catalysis, on the simple redox organic transformations and applications of this transformation to the synthesis of several heterocycles, or using specific metal complexes or coordination, 1D, one-dimension coordination metal-based polymers for the same exactly synthetic strategies. In details, we are interested for synthesis of several N heterocycles like pyrazoles or even pyrols or even pyridines or the hydropyridines molecules using the chemistry of materials and to apply this chemistry to the synthesis with the simplest way under mild conditions, under, for example, sustainable conditions. And for this reason, we focused on this simple redox transformation to the nitroarenes to the corresponding amine, or even amine to the corresponding intermediate nitroso or N-Aryl hydroxylamine. Alongside the last 5 years, we are also interested for the photoirradiation chemistry using polyoxometalates or gold nanoparticles for the same exactly synthetic approaches. For example, to the synthesis or redox, even redox transformation of amine to the nitro or nitroso intermediate, or to the synthesis of N-oxo heterocycle molecules, or even in the simplest oxygenation of unsaturated hydrocarbons. Today I'm going to focus on the synthesis of N-Aryl hydroxylamide, and for this reason I would like to show you this simple reduction process. If someone like to follow these reduction processes, then you will recognize immediately that when you try to reduce the nitroarene, you will observe, instead of the simple and common intermediate nitrosoarene or N-Aryl hydroxylamine, instead of these intermediates, then immediately you will see that in most cases you will observe the corresponding dimers as byproduct. The dimers like azoxyarene, azoarene, or hydrazoarene. And in case that you would like to reduce or to decompose these, degrade these dimers, then you need, for example, or 100% you need hydrogenation processes in order to achieve the desired aniline. In our case, we're interested not to observe the corresponding anilines, but to stop the reaction until the N-Aryl hydroxylamine intermediate. This intermediate is a versatile organic molecule, and it's very useful for as intermediate for the synthesis of several biological active molecules. So we're interested for observe or selectively synthesize this intermediate instead of its further reduced and obtain the corresponding aniline. So having this in our mind, and also have also in our lab our recent collaborative work for the cobalt catalyzed nitroarene to the corresponding anilines using methyl hydrazine as the reducing agent. We observed that especially when we use nitroarenes substituted with electron deficient group like ester or cyano or ketone groups, then at initial time reactions, we observed as the major product the corresponding N-Aryl hydroxylamide, but then in a faster way, it's reduced further to the corresponding imine. So can we synthesize selectively this unstable but very useful intermediate N-Aryl hydroxylamide using, for example, a clean and mild process, high yields, even a catalyst-free pathway, but not under thermal conditions, but using photo irradiation conditions? And the answer is probably yes. We were able to do this, and today I'm going to present you two different methodologies. The one contains the catalyst-free photo-induced synthesis of N-Aryl hydroxylamine, and then to the corresponding probably indoors. But we are going to focus on this selective transformation using UV visible conditions and methyl hydrazine as the reducing agent. These results, we are lucky that we already published an organic letter 1.5 years ago. And also the same exactly procedure we also tried to perform under milder conditions and using a ruthenium complex as a photosensitizer in the presence of white LED apparatus. This is an unpublished result, and we hope that we can publish as soon as possible. So far in the bibliography, it was known that nitroarenes under thermal conditions and using several metal nanoparticles or nanotubes, for example, gold, platinum, nickel, or rhodium, can lead to the N-Aryl hydroxylamine in good yields, thermal conditions. Photochemical conditions, only one paper appears in the bibliography using this green Hans ester as the reducing agent. So we wonder that, can we do this? Can we use our conditions with methyl hydrazine and acetonitrile as the solvent to do this transformation selectively? And we start our story, first of all, to find the conditions for this photo-induced reduction processes. And as you can see, in cases that we use the common that we already use in our laboratory complexes, metal catalysts, or even common photosensitizers like dicyanoanthracene or osmegal, in all cases, a mixture of the corresponding N-Aryl hydroxylamine with the corresponding aniline, a mixture was observed. To our surprise, when we did the blank experiment without any catalyst, using only methyl hydrazine and acetonitrile as the solvent, then we observed the formation of the desired intermediate as the only product. Then, changing the reducing agent, for example, from methyl hydrazine to phenylhydrazine, then we were able to observe exactly this selective transformation, but in lower yield, and lower yield also observed using dimethyl, 1.1 dimethyl hydrazine, but in this case, we also observe the corresponding azoxy as a byproduct. In cases of hydrazine, diethylene hydrazine, or tosyl hydrazine, or even hydrogen bubbling reaction under these conditions without the presence of methyl hydrazine, then no reaction was observed. So continue to evaluate our our optimized conditions. We found that no any other hydrogen source, hydrogen reducing agent, compound that can give a hydrogen, found that can catalyze this, can transform these reduction processes. And also, to our surprise, and this is make our conditions more available to the organic synthesis, is that this reaction also works not only in acetonitrile, but also in other protic or non-polar and aprotic solvent like ethanol or dimethyl carbonate, or even tetrahydrofuran or dichloroethylene, or even toluene. So, having all these results in our hands, then we continue to apply this optimized condition using acetonitrile as the solvent and only methyl hydrazine to a series of nitroarene substituted even with electron-rich moieties or with electron-poor moieties. And you can see in all cases we observed high isolated yields and of course in a reaction time between 1 hour and 3 hours, more or less. The most important thing is that we found an interesting application of this methodology to these two antibiotic molecules, the azomycin and chloramphenicol, that we were able to reduce selectively the nitro group that contains these two molecules to the corresponding N-Aryl hydroxylamine. And this molecule represents one of the byproducts during the pharmacological synthesis, during the synthesis of this kind of antibiotic molecules. And having all these results, we continue to elucidate a mechanistic pathway for such interesting procedure. And firstly, we add some quenchers into the reaction process, for example, dicyanoanthracene or trimethoxybenzene or even tembo, that is a free, tembo is a free radical scavenger. And as you can see, especially in the last two cases, not a significant decrease of the yield of the desired N-Aryl hydroxylamine was observed. Instead, in the first case, that when we added the 9.10 dicyanoanthracene, then the reaction is retarded, for example, to 50%. So this means that probably we have a proton-coupled electron transfer, but we have to continue and to see also if in case that the byproducts azo, hydrazo, and azoxyurine were formed, if can reduce under this condition to the corresponding desired N-hydroxylamine, but no reaction was observed. So this is for sure support that is an evidence or support that during this process we don't have this condensation route. And also this is found support from the UV-Vis spectroscopy that we also observed the decrease of the absorptions of the amine and the increase of the N-Aryl hydroxylamine during the reduction processes. The most important thing is that nitrozoarine, that is the second intermediate that you can observe during the reduction processes, can be formed. And why I'm saying that can be formed? Because nitrozoarine under methyl hydrazine and not need of any photoirradiation conditions, then we found that it can be reduced to the corresponding N-Aryl hydroxylamine very fast, almost within 15 minutes, and gives the desired N-Aryl hydroxylamine in high or most quantitative yield. So this is probably the last pathway of our proposed mechanism, but before that, we are interested to find the lack of methylhydrazine. Methylhydrazine, as you can see, monitored by proton NMR, is transformed to the corresponding 4-methylhydrazone. This is the NMR of this decomposes product of methylhydrazine, but also methylhydrazine during the reaction conditions decomposes to methane and nitrogen, as we detect by GC-DCD, gas chromatography with thermal conductivity detector. Also, this reaction found support from our reduction using phenylhydrazine and monitored the reaction by proton NMR that we observed the corresponding benzene as the byproduct from this reducing agent like methane, as we detect with gas chromatography. And finally, we were able to propose this plausible mechanistic pathway that contains, first of all, the excitation of the nitroarine, and then in the presence of methylhydrazine through a set or a HAT, hydrogen atom transfer, never know, hydrogen atom transfer processes to produce the corresponding N-Aryl dihydroxylamine that we didn't observe, of course, but probably this is dehydrated too fast, giving the corresponding nitrosoarine, that this is fast transformed to the corresponding N-Aryl hydroxylamine without the need of the photo irradiation conditions under thermal conditions. So this was the proposed so far mechanism, and this is published to the organic letter 1.5 years ago. And for the second part of my talk, we would like to continue this selective reduction process using milder conditions, not exactly the UV area, but moving to the visible area using ruthenium photocatalyst that you can irradiate it at more or less 450 nanometers, that this ruthenium catalyst is able, through a metal ligand transfer, to gives you a reductive cycle that we would like to do this. And having this in our mind and searching also the bibliography, we found that there were 3 studies on these reduction processes, but as you can see, all of them propose the formation of the corresponding aniline. No selective synthetic processes was reported so far to the corresponding N-Aryl hydroxylamine. So, having also the experience from our previous work, we tried, first of all, using acetonitrile, methylhydrazine, and in the presence of ruthenium catalyst, this kind of selective transformation. And as you can see, I'm not going through in details for all these reaction conditions evaluations, but as you can see, this reaction is optimized to have this ruthenium catalyst in 1 mol%, methylhydrazine in 5 equivalent, and acetonitrile as the solvent, and using an apparatus with 10 watt white LEDs, then we were able to synthesize again to obtain and isolate the corresponding N-Aryl hydroxylamine in high yield and in milder conditions in this case. Further application and mechanistic studies are in progress to support our new catalytic cycle. And for this reason, I'm not going through in details to these mechanistic studies because now a lot of experiment and also theoretical studies are running for this kind of selective transformation. So I would like to conclude and I would like to thank you. I would like to remind you that using light and catalyst-free or even using of ruthenium catalyst under milder conditions, we were able to selectively reduce nitro compound to the corresponding N-Aryl hydroxylamine and then further to obtain probably as we recently found in our laboratory that we can transform the corresponding nitroarenes to the corresponding indoors enterocycle. So I would like to thank a lot of people, of course, my collaborator and especially Dr. Michael Lykakis that responds, that is the guy that mainly works on this selectively field, and also all of my group that is still working on this selective synthesis of N-heterocycle using even metal nanoparticles or even light. So I would like to thank all these people. Here is Dr. Lykakis that work on this field, and of course all of my team, and of course you for your attention. Thank you very much.